Okay, I guess we're in business. Sorry. A bit late. So we have about 10 more minutes of the topic from last time left to do, and then we'll start on what I really wanted to start on this morning. We've been talking about the nervous system in general. We talked a little bit about, we introduced you to the anatomy of the nervous system. We talked a little bit about nerve cells, showed you what they look like, and talked a little bit about how they work, about action potentials and resting potentials, and EPSPs and IPSPs and whatnot, and a little bit about how they're used. And we're going to be using that information in various ways as we go through the course. But the last thing I wanted to do, although it probably won't bear very much on anything else in the course, but I still want you to know something about it, is how these resting potentials and action potentials and so on are generated. A little bit about what's going on there, because it's not magic, it's very, very well understood. And so I just want to give you a little bit of an introduction to that, and that's what we started at the end last time. We started out, we reminded you about these rules from physics or physical chemistry or wherever one thinks of them as coming from. So we talked about electrostatic forces, about ions, so on and so forth. Just reminded you, you'd all been exposed to that stuff before. I can't remember exactly where we ended up, but let's start right at this point. Suppose we have a situation. Oh, sorry. I guess I told you this. I told you that the ions that are important, or some of the ions that are important to the functioning of nerve cells, are sodium, chloride, potassium, and these large organic ions which have a negative charge, which are usually referred to as A-. Suppose, for starters, that we imagine that there's sodium and chloride outside, and there's A- and potassium inside, and there's an equal number of these and these, so that charge balances out. There's an equal number of these and these, so that charge balances out. There's an equal number of these and these and these and these, so everything's electrically neutral everywhere, for starters. Okay. Now, keeping these rules in mind, suppose that we now open up the cell membrane so potassium ions can move back and forth freely. Are they going to stay inside? Are they going to move outside? What are they going to do? What's going to happen to potassium ions? Somebody want to hazard a guess or just shout it out or whatever? It's all right? Well, no, don't do any chemistry for me. Just what's going to happen to the potassium ions? They're going to stay there or they're going to move? So, what? All of them are going to stay inside. Okay. Let's see. Let's remind ourselves about these rules. Electrostatic forces, yeah. As far as electrostatic forces are, they are going to stay inside. There's nothing dragging anything anywhere or pushing anything anywhere from electrostatic forces. Diffusional forces. What are they going to do to potassium ions? They're going to go out because there's a lot of them inside. In fact, that's the only place they are. There's none of them outside. They're moving around at random all the time. Some of them are going to go out. Okay, so some potassium will go out. Now, next question. Will they go out so much that eventually there is an equal amount of potassium ions inside and outside? How many say yes? How many say no? Those of you who say no is the correct answer. Why did you say no? I told you can guess, and that's fine, but I bet somebody has a reason. Yes?
Because there's already sodium ion on the outside.
Sorry, say that. Speak up a little bit more.
Outside the membrane, there's sodium ion.
Yes, right.
Already, so there's enough positive charge. So potassium will not.
Okay, so potassium's going to go out, and it's going to make things more positive outside, And as that keeps happening, eventually, things started out all equal everywhere. But as the potassium goes out, the outside's going to get more positive, the inside's going to get more negative, and there's going to come a point where the extra positivity outside is going to prevent, or is going to discourage, work against potassium ions going out. So they're not all, you're never going to get to a point where they go out so much that you have an equal number of potassium inside and outside. So you're going to have some potassium leave for diffusional reasons, but they're not all going to go out, or not even, never mind all, they're not even going to get even on the two sides, because as they're going out, the outside's getting more positive, and that's going to tend to repel them going out. So it's going to be somewhere in between. So the inside will now, therefore, become somewhat negative. It started out, everything was zero. There was no voltage difference across the membrane, but now because we've got the positive ions going out to some extent, I'll get you in a minute, the outside's going to become more positive, and inside's going to become more negative relative to it. By the way, a convention, something I forgot to mention before, one can talk about the voltage of the inside relative to the outside, or one can talk about the voltage of the outside relative to the inside. Physiologists and neurophysiologists all adopt the convention of talking about the inside relative to the outside. So if I say the voltage of this, the potential of the cell is minus 3 millivolts, what I mean is the inside is 3 millivolts negative to the outside. That's just understood. Yeah.
Doesn't that assume that sodium ions are simultaneously using?
The only thing the membrane is open to is potassium.
Oh,
that was
okay,
our rule.
right, okay.
Not open to everything, just open to potassium.
Oh, thank you.
Yeah. And it turns out this kind of selective opening up of membranes goes on. That's a major deal in the functioning of the nervous system. So the inside will be negative. Well, that in fact is the explanation of the resting potential. That is the explanation of the resting potential. That's exactly what happens. The cell at rest there's a little bit more to it, but basically the cell at rest is somewhat open to potassium ions, selectively open to potassium ions, and that's what happens. So that's that. Okay, so we just answered those questions. Now we have our resting potential. So we've got the inside negative relative to the outside somewhat. And we've got some potassium outside, probably still more potassium inside, in fact. Doesn't take, once not too much of it goes out, it gets pretty discouraged. And so you actually end up having, at the rest, you have a lot more potassium inside than you have outside. Suppose you allow the membrane, in addition to having this picture, suppose you, in addition, open up the membrane so sodium can go through. But you just do it for a short time. Just open it up a little bit. First of all, what's going to happen to the sodium ions? Are they going to stay there, or is some going to go in? In, right. And what is that going to do to the membrane potential, the inside relative to the outside, relative to this baseline that it's currently at? It's going to go. Is the inside going to go more positive or more negative as a result of the sodium coming in? Positive, of course. So what's going to happen is that if you briefly open up the sodium, some sodium is going to go in, and that's going to make the inside go a little positive relative to the resting potential. That's the basis for EPSP. Okay, that's exactly what happens during EPSP. Goes a little beyond this course, but as these ions are moving around, there are some pumps that can move them back again, and that happens. But that's a very slow process, so we don't have to worry about it. And moreover, when sodium goes in, as I just described, it takes very little to go in to make a rather large voltage difference. And the amount that goes in is so small relative to the amount that was out here that you can forget about it, except unless you do it over and over and over and over and over again. So we talk about sodium going in, but it just goes in a little bit. Doesn't change very much the concentration of the amount that's left outside. Okay, so it goes in or depolarizes the cell. Okay, so that's the basis for EPSPs. Suppose, okay, well, what I said, excitatory input to dendrites, the excitatory transmitter causes a slight but brief sodium opening, and this is the basis for EPSP. So that's what I just said. Okay, now there's another rule. It turns out there's another thing that can open up sodium channels. They're actually a different, slightly different kind of sodium channels, but they're sodium channels. Another thing that can open up sodium channels is a sufficiently large depolarization of the membrane itself. If you depolarize the membrane enough past some critical firing level, which you've already heard about critical firing levels, if you depolarize it past some threshold or some suitable critical firing level, that in itself opens up the membrane to sodium. And so these are called voltage-sensitive sodium channels. And so that, of course, causes sodium to come in. Moreover, that keeps going. And in fact, it's a vicious circle because the depolarization allows the sodium, the depolarization opens up the membrane to sodium, which allows sodium to come in, which depolarizes inside, which makes the inside even more depolarized, and it's a vicious circle. And so you get so you get sodium going in until there's a very large voltage shift. Not very much still comes in, but it's enough to make a big voltage shift, making the inside much more positive than it was before. And that is the basis for a spike. The reason the spikes don't last forever is that this process, these sodium channels get tired. And they stay open for a little while, long enough to get a pretty big depolarization, and then they conk out. There's a little bit more to that too, but that's good enough. So that's why spikes don't last. That's part of the reason why spikes don't last forever. There's also a bit more to it, but we don't need to concern ourselves with that in this course. So it basically, for our purposes, it stops because the channels tire out. Some other things happen too, that if some of you somewhere along the line know something about this, you'll know about that too, but we don't need to talk about it. Okay, so we now know the basis for resting potential, EPSPs, and spikes. We're not going to talk about inhibition, the details for inhibition, but it's a similar kind of story. Okay, that's all you need to know about this sort of physical chemistry of or whatever you want to call it, of producing these membrane potentials. I just wanted to take some of the magic out of it. Okay, so let us review now where we've been in this block of lectures. And a few of the things I'm going to say here, I didn't really say explicitly during the lecture, but if you think about it, they're implicit during the lecture. And in actual fact, a very good way to review, or one very good way to review these lectures, this last block of lectures, is to think of yourself what the things I said were that lead to each of these statements. That'd be a good way to find out, to get a sense of whether you understand it. And that's really what you should be doing anyway. Okay, first point. This is not in the order I presented it, but during the lectures. Okay, the nervous systems in general, are made up of synaptically interconnected nerve cells that do logical operations and determine our behavior in response to needs, situations, and events. We saw something of how they work. That's kind of what we did last. Point 2. Different information processing or computational jobs are done by different separate neural circuits designed for those particular tasks. So we'll see some more of that in a few minutes. These are often in spatially separated locations in the nervous system. So they're not necessarily, usually they're not sort of all mushed up with one another. They are separated, though not always, rather than being all mixed up together. And this is what we refer to as modularity. Thirdly, to a considerable extent, the nervous system evolved by adding new circuitry on top of, and that is to say, rostral to old. The new circuitry, and that much we did say. The new circuitry builds on the capabilities of the old and makes use of these abilities. We didn't quite say that, but you should be able to kind of see some examples of why we say it. The old circuitry, of course, becomes modified to integrate it with the new. We didn't say that, but it's true. But to some extent, the older, more causal circuitry continues to be competent to do things even without the newer, more rostral parts of the nervous system. Thus, even the spinal cord by itself can produce some meaningful behavior. That we've talked about a lot. Thus, even the spontaneity of behavior depends heavily on parts of the brain above the level of the midbrain. We talked about that. And adding the hypothalamus to a decorticate animal turns it into an animal that can organize behavior effectively for survival. We talked about that. The cortex itself is essential for sophisticated sensory analysis, fine motor activities, and planning and foresight. We talked a little bit about, we mentioned that. But it is not necessarily required even for some very sophisticated abilities such as learning. And we did talk about that a little bit. And we'll talk about that some more later Okay, so this is sort of a summary of sort of the take-home messages from where we've just been in this little block of lectures so far on the nervous system. Okay, so from now on, we're going to assume you know that stuff, and we're going to go on and use it in a certain way. Now, there's an awful lot of stuff we could in principle, talk about. This is the whole subject of behavioral neuroscience, and one could easily, and we do, give courses on that. And these courses generally include a study of how sensory processing is done, how movement is produced, how drives and motives are created, are brought about, all kinds of stuff. We're not going to have time to do all that in here. For whatever reason, for reasons of my own, am going to talk about sensory processing specifically, and specifically vision. And the reason I'm doing that is written down right here. Study of the visual system, which is probably the best understood part of the brain, provides an arena for looking at a host of things that apply to everything the brain does. This includes how information is coded, how neural computations are done, how decisions are made, and how our conscious perceptions are formed. Now, we are, of course, as far as working, the most important thing to any and all of us is our conscious, what's going on in our own heads. The area in which we know some of the very most about that is in the study of vision. You will see that whereas that is the area that we know the most about, there's an awful lot more that we don't know about it. And giant gaps in our knowledge, but it's still the best place to discuss these things, and so that's what we're going to do. Okay, so here's our little outline of how we're going to proceed. We're going to first talk a little bit about the anatomy of the visual pathway, which in its own right I don't care about, but you're going to have to know this in order for us to discuss other things. The fact that you don't have to know it as an end in itself doesn't mean I won't ask you questions about it on the exam. I will. Secondly, we're going to talk about what nerve cells at various levels of the pathway do. That doesn't make sense quite yet, but it will in a few minutes. Then we're going to talk specifically about modularity in the visual system. We've talked about modularity in the abstract. You'll see some very nice examples of it in the visual system. Then there's going to be a rather long section on something that I think is very important and very interesting. There is a natural tendency to assume that our mental image, our perceptions of the world out there, are sort of kind of funneled in, and it's a direct thing. And for many years, philosophers and scientists kind of thought that. But it turns out that's absolutely dead wrong. It turns out that everything we see or perceive or hear or whatever perceive is constructed by our brain. The total construction of our brain, using evidence that it gets from outside, that the brain gets from outside. But it's a highly indirect process. We create our image of the world. Those of you who are philosophy majors know there's a lot of discussion of that kind of stuff in philosophy. And it turns out it's right. We don't know the world. We do not have any direct knowledge of the world. None. It's all a construction of our brain. Fortunately, the system works pretty well, so so our perceptions do bear a very good relationship to the brain, but it isn't in a direct way. It happens in a very indirect way, and we will see lots of examples of that in this little block of lectures. And then finally, and we were in talking about these things, we're kind of talking about consciousness a little bit, sort of. But then I want to address specifically what the neural correlates of consciousness are, because as we will see, there's lots of information processing that your brain does, and lots of behavior that it can produce without conscious mediation. We've seen one example of that already in talking about the flexion reflex, but there are lots more examples, and we'll talk about some of those. Okay, so that's where we're going over the next 3 lectures. Okay, the visual system. It starts in the eye, as you might expect, on the retina. The very first cells that light encounters, first cells that I don't want to say it that way because that's actually not quite accurate. At the beginning of the information processing stream, the first thing that happens is that light affects visual receptor cells. There are a number of different kinds of those, and we'll talk something about that later on. Now, these visual receptor cells are spread all over your retina, what happens is an image formed by the lens of your eye gets projected on the retina. And this is my crude representation of the retina. Yes. So these receptor cells in the retina then project to a layer of so-called bipolar cells. The bipolar cells, in turn, project to a layer of so-called ganglion cells. There are some cells that interconnect these guys from connecting between one place and another at a given level, at a given layer. So there's cells that make lateral connections back and forth this way, here, and here, and some more here. And these are things like horizontal cells and amacrine cells. But what I want to focus on right now is this downward flow. So receptors to bipolars to ganglion cells. This is all in your retina. And then the ganglion cells, it's the axons of the ganglion cells that form the optic tract that goes to the rest of your brain. And so this shows these cells funneling down into the optic tract. Okay, now these axons go two different places. On the one hand, they go to the superior colliculus, which you now know about. And there's actually interesting stuff, lots of interesting stuff that happens there. And that pathway actually allows you to some extent to see and to produce behavior in response to visual stimuli. But we're not going to talk about it. The other place they go is to a pathway that's going to lead to the cortex. And the first place they go there is they go to the thalamus, to a particular part of the thalamus known as the lateral geniculate nucleus. I'll show that to you over here in a minute. From the lateral geniculate nucleus, they go to the cortex. And in the cortex, there are a whole bunch of different visual areas. This is actually not all of them. There are probably about 20 or 30 different visual areas, each of them doing a different job. That's one of these examples of modularity that I talked about. But we're just going to talk about some of them here. And some of the most important ones. And the first place they go is to what's called the primary visual cortex, which is a term I don't have here. Is it here anywhere? It's not here anywhere. A primary visual cortex, which is also called visual area 1 or just V1. That's the most common term for it these days, V1. And then from V1, we go from V1 to V2, from V2 to, there's no V3 on the picture, but there's a V3, eventually to V4, and then to a region called the inferotemporal cortex. I'll show you where these are in a minute. But it's not a straight line. There are other routes. So V1 also goes to another area called area MT, which in turn goes to yet another visual area in the parietal lobe, known as the parietal visual area. Not only does V1 go to MT, but so does V2 go to MT. Okay, so that's the pathway. Now, we're going to be talking about what goes on in this pathway, starting in a few minutes. But one very important thing that I want to point out to you right now, before I forget, is you see these green arrows. They're in the backward direction. So just as the lateral geniculate projects to V1, so V1 projects back to the lateral geniculate. And it's not that a lot of nerve cells, it's not just that a lot of axons go from the lateral geniculate of the thalamus to V1. There are just as many or more going backwards as forwards. So it's a very, very big pathway. So lots of neurons going backwards. We are only just beginning to understand what those backward pathways do. But they must be important because it's a big pathway and they must be doing something. So figuring out what they do is an important thing. We'll touch on that in various ways as we move along. Okay. So now notice I put some of these forward-going arrows in red and some in blue, and that's because there are in fact considered to be two different streams of visual information processing, or two different streams of cortical processing. Another example of modularity. And I've drawn that up here. Let's actually look at what some of these structures are. So V1 is in the back of the brain in the occipital lobe. We already kind of know that. In front of that, there's V2. You don't know that's where V2 is, but it is. That's also in the occipital lobe. Then here's V4. Oh, that's the temporal lobe. Never mind. Here is the, so I didn't quite get to the bottom now. Okay, there's V4. Here is the parietal visual area. On the inside surface of the temporal lobe is the this area MT. And I think I forgot to say this. Let me say it now again if I didn't. V4 projects to the last part of the visual, sort of the last stop in the visual system, called the inferotemporal cortex. And once you go beyond inferotemporal cortex, you're getting into circuitry that has to do with controlling behavior. It's not just sensory processing. So inferotemporal cortex is the last stop there. The parietal visual area is the last stop here. Anyway, here are where these structures are. Now, I've drawn both the red and the blue. And that's because these are two different streams of visual processing that do different things. The dorsal, let's talk about the ventral stream first. The ventral stream is often referred to, I got the wrong set of slides up here. I've modified them. Maybe I modified it on the next slide. I hope so. Anyway, this should say, and I fixed it this morning so it did say, but maybe I modified the wrong set of slides. The ventral stream is also sometimes called the what stream, and the dorsal stream is sometimes called the where stream. What and where. The what stream has to do with analyzing what the thing you're looking at is, and also its details of its shape, its color, things like that. The where stream, the dorsal stream, is concerned with analyzing where in the visual field the object is. Is it over here or over there? The what stream doesn't care about where it is. It only cares about what it is, not where it is. Vice versa. The dorsal stream doesn't care about what it is. It only cares about where it is. So it's concerned with where in the visual field the object is, or where in space the object is, which comes to the same thing. It's concerned with movement and the direction of movement. So if you have moving objects, it's the dorsal stream that's recognizing the movements and analyzing the direction. This is bothering me just a minute. Let me just look ahead a minute and see if I've modified a slide up here. Oh dear. Something bad's going to happen down the line, but we'll worry about it when it happens. Okay, and here's a real picture of the brain that you can use to try to figure out where these things really are. It's a little bit oblique. It's not. This is a strictly side view. Also, it's drawn by me, so it's a pretty bad picture. This is sort of an oblique view, but here's a cerebellum back here. Here's the caudal end, back end of the brain, which is back here. So this is V1 in yellow. And then V2, light yellow. Then V2 here's in sort of orange or dark yellow. V3, V4, what's V4? V4 is right. I can't even tell what V4 is. That's not this yet. I don't know. Anyway, figure it out. You may be helped in this. I can't remember where I got this picture from, but I don't think it's from your book. There's probably a good picture in your book, too. Anyway, so those will allow you to make some relationships. Now, what we're going to do next is to look and see what sorts of... Yes?
Is there a reason V3 isn't on your diagram?
Huh?
Is there a reason?
No, I didn't put V3. I don't remember why I didn't put it there, but it's not there.
And the superior...
Because I'm not going to talk about it, that's why. Yeah.
Okay, the superior colliculi is the rostral part of the
tectum? It's dorsal tectum.
Okay.
Dorsal tectum. Right. The roof of the tectum. Sorry, dorsal midbrain. The tectum of the midbrain. The roof of the midbrain.
Okay, yeah. All right.
Well, you all, yeah, so I sent you all your little anatomy half a dozen anatomy questions. It wasn't worth making an answer sheet for. You just do that on your own. There will be some answer sheets for some later questions that we'll get, but those were just so simple that I didn't think it was necessary. And the answer sheet, when you look at it, you'll see there's no explanation. There's just the answers. So don't look at it, but you use. I wouldn't try to do those anatomy questions until you yourself think you've studied enough so you know it, so you can use it as a little test for yourself. It's not like the other step where there's some back and forth. The more complicated things, you may want to go back and forth to some extent, but that one, you should try to master it first and then take the quiz to check yourself. Anyways, so we're going to talk about what nerve cells some of these stops along here do in both the dorsal and the ventral streams. Okay, let's start up here in the ganglion cells. Well, sorry, let's go back. I should have that on. Let's start at the ganglion cells. So let's start by recording either from the ganglion cells themselves or from the axons of the optic tract. In the picture here, I think I've actually shown us recording from the axons of the optic tract. Now, what happens is, if you have the retina here, and you've got all these little ganglion cells spread all over the place, and what happens is, at a given spot on the retina, the cell that's stimulated is one that was stimulated by the bipolar cell in front of that, and the receptor cells in front of that, and basically the retina obviously is sort of a map of the external world, which gets projected by the lens of the eye onto the retina. That much is kind of obvious. What's maybe not quite so obvious is that when you get into the optic tract, that same arrangement continues. In other words, two ganglion cells that are close together on the retina will have their axons close together in the optic tract. And that is referred to as a topographic representation. That is to say, things that are close together in the one representation are close together in the other representation, or we sometimes call it a visiotopic representation. So things don't get scrambled spatially when you go into the optic tract. Two ganglion cells that are close together in the retina have their axons together, close together in the optic tract by and okay. So suppose that we shine little spots of light on the retina. Or that something looks at little spots of light out in the world. It comes to the same thing because the lens focuses it on the lens of the eye focuses it on the retina. Let's look at the left-hand side first. So suppose we put a spot of light there. It's not a red spot of light. This is just to indicate for us to switch a switch. So suppose we put a spot of light right there on the retina. Here on the optic tract is the ganglion, or will be ganglion cells, or a ganglion cell that will respond to that light. If we move our spot of light to a nearby spot, then it will activate different receptor cells and different bipolar cells and different ganglion cells. And those will therefore activate different axons in the optic tract, but those axons will be close to the ones that did the red spot, because that's the visiotopic or topographic representation. If we go far, on the other hand, if we shine the light far away on the retina, then the spot on the optic tract will be different. Now, just so you don't get the wrong impression, I've drawn this so that the general orientation here is the same as the orientation here, but in fact, the retina or the optic tract might well get twisted, so that this might be upside down or sideways or at some angle with respect to this, but nevertheless, two things that are close together here will be close together here, and two things that are far away here on the retina will be far away on the optic tract. Now, another interesting fact is that for any given location on the retina, you activate certain ganglion cells that will be close together, also close together in the retina, and that will have axons that are close together in the optic tract. But you will have for any given small spot, you'll have two different kinds of ganglion cells. Ones that are called off cells and ones that are called on cells. One kind responds to brightness, and the other kind responds to shadows. One kind responds to brightness, and the other to darkness. Now that seems kind of a waste to double everything up like that, but if you think about it and think about the way nerve cell signal activity, you can begin to say that it makes a great deal of sense for the nervous system to do it that way. Suppose we had just one kind of ganglion cell. So here it is. It's one a dual-purpose cell. Suppose it had a low spontaneous firing rate. So it's firing only when you do something to it. Well, if you shine a light, suppose it's a cell that responds to light, brightness. Suppose that's the only kind you have. You have ones that respond to light. So you shine a light on it, and it goes from not firing very much to firing a lot. That's easy for cells downstream to detect. Because you've gone from this kind of firing to that kind of firing. But suppose you shine a shadow on that same spot, and this is the only kind of ganglion cell you have. What's going to happen, it'll go from this low rate to a zero rate. But for a cell downstream to make a distinction between this and that is very hard. It'll take a long time to figure out whether the rate has really gone down, because there wasn't many spikes per second occurring anyway. And so that's not going to be so great. Well, it'll go the other way around. Perhaps you can have one kind of cell with a high spontaneous rate. You've got exactly the opposite problem. Now you could build a system with an intermediate size, intermediate spontaneous firing rate that would increase its firing, say, to bright and decrease its firing to dark, but that's not the way that but because of this problem, the nervous system gets much better sensitivity by, in fact, having two different kinds. One kind that has a low firing rate and increases its rate a lot for darkness, and another kind that has a low spontaneous rate and increases its rate a lot for brightness. So we have on cells and off cells. And so that's how the nervous system, how the visual system and other parts of the nervous system do this kind of thing. We'll often differentiate cells into things that go up and things that go down. One channel carrying the up information and the other carrying the decreased information. And that's not only true in the visual system. That's true in places like the motivational system, which we're not going to talk about. It's true all over the brain that kind of trick is often, not always, but often used. Oops, what is that? Could I really that? That wasn't that one slide. How did I do that? Oh. Good. Okay, so we've been talking about the ganglion cells. Now, I'm not going to talk about the thalamus. Things go from the ganglion cells to the thalamus, and from the thalamus to V1. I'll talk a little bit more about the thalamus in a few minutes, but let's just skip the thalamus for a moment. We go up to V1. Picture changes quite a bit. Suppose that, here is the visual field, or the retina, and here, imagine, is cells in V1. And suppose we start with a little spot of light, just like I did with the retina, and I'm going to portray what the cells are doing. So the cell, I'm recording. Let's say I'm dealing with I'm recording from this red guy, right there. I put an electrode. By the way, I should mention, we talked about putting electrodes inside the cells, but this kind of experiment is not usually done by putting the electrode inside the cell. It's done by putting it right next to the cell, just outside the cell. And the reason for that is that it's very hard to keep electrodes inside cells without damaging them. So we put it just outside, and what happens is action potentials involve currents flowing into cells, and you can even these electrodes outside cells can detect that current flow a little bit. If anybody remembers about Ohm's law from physics somewhere, that's the reason it happens. You don't have to worry about that. In any case, you can detect these action potentials we're recording from this red guy here, and we can detect the action potentials if it's firing. And so I'm not doing anything, no stimulus. And so it's pop, 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 pop. And now I shine a light over here. Pop, 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 pop. Oops, sorry. I don't shine the lights on the brain. I shine the lights on the retina. Excuse me. Go back over here. Pop, 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 pop. But I'm recording from that guy there. Pop, 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 You get the picture. So if I shine the light along a line, a short line, with a particular orientation, that's what makes this red guy fire. If I go nearby, I will find a cell that will be very similar, except that it will like that line. Go to another nearby spot, and I will find a cell that likes that line. And in fact, the way these cells are arranged is in a very precise way in terms of the angles. What the best angle is moves in a very systematic way across the visual cortex, but we don't need to worry about that right now. So cells in the visual cortex respond to things occurring at a given location in the retina, but also they respond to edges or lines, contours, with particular orientations. Each cell having a particular orientation that it likes best. Over here, same story, but another differentiation is there are these line detecting cells for bright lines and different ones for dark lines. Same story as in the ganglion cells of the retina. We have the bright detecting system, or the on system, and the dark detecting system, or the off system. So just to sort of compare V1 and the ganglion cells in the retina, if you're looking at a cup like this, in the optic nerve, a firing of this cell says there is a dark spot, the edge here, at a particular place near the center of the retina, a projection onto the retina of this coffee cup, which is right there, sort of in the center of the retina, the way I've laid it out. That's relevant information, of course, but the V1 gives you much more precise, much fuller information. It says there is something at this spot on my retina, and moreover, it is the contour has a particular orientation of sort of whatever this is, sort of more rough, a little off horizontal, which is much fuller information. Think about an artist making a sketch. Artists often do things, make little sketches, little line segments, and that's exactly what V1 is doing. And in fact, some visual neurophysiologists refer to the V1 representation as a primal sketch because of that parallel to what an artist does when they're making a sketch. Okay, now how does it happen? How does it work out? How is it that how does it come about that the cells in the retina, which respond to little dots of light, little spots of light, how does that representation get transformed when we get to V1 so that the cells respond to lines rather than spots? And the answer is spatial summation, exactly the way the circuitry is. So first of all, let's talk just briefly about the lateral geniculate. It turns out that for our purposes, the activity of the cells in the lateral geniculate pretty much mirrors that in the retina. That's not entirely, that's only approximately true, but for our purposes it's good enough. And so if we have let's say this red line of light, or darkness as the case may be, let's say light, shining on the retina, that will activate a row or column of cells, a line of cells in the lateral geniculate, and a cell in the cortex that responds to that particular orientation of line will get input from these 1, 2, 3, 4, 5, 6 guys in the picture. Of course, there's many more than 6 in real life. So that's why this cell responds to this orientation, because it gets input, excitatory synapses from this group of cells and not others. Yes?
Do other cells reuse the same cells, other lines? Do you have multiple?
Well, if you had 2 lines that, they reuse these guys, but they don't reuse these guys.
Yeah. Okay. So there can be multiple intersections. It has to be all.
Up here, these guys get used over.
Okay.
But these guys don't.
Okay.
These guys are private. They are dedicated. this cell is dedicated to signaling that there is something with a particular orientation at this particular spot, period. It does nothing else. Okay, and then the other picture. But it's a little bit more complicated than this. We talked about these backward projecting pathways, and this is the one place where something is known about, or not, it's one of the places where a little something is known about what they do. Although I'm told by my by my colleagues that really do know something about the visual system, which I don't, that this experiment is a little suspect, but I believe it anyway. Okay, so here is there's a backward pathway. It turns out this ganglion cell, sorry, this V1 cell, or a cell that's connected to it, it's not really necessarily the very same one, projects back to the lateral geniculate. That's that backward projecting pathway we talked about. Turns out the way it does it is not just helter-skelter. This cell projects information back to precisely those cells that gave information to it, and not others. The effect of that is to cause a positive feedback loop, so that if you give a kind of a lousy, faint, low contrast, noisy line segment, which I put here in pink instead of red to indicate that it's faint, that activates these cells, but doesn't activate them very well. And so it activates this cell, which doesn't activate it very well. It fires a little bit. It sends a signal back here which reinforces the activity. And before you know it, you've got a much stronger signal than you otherwise would have had. There's a chance it may make a mistake because it was a noise signal, but it enhances the signal. And so you can do things to stop this backward pathway. If you do that, if you do that, the response of that cell to a weak stimulus, which would have looked like that when the animal was intact, when you bugger up that pathway, instead looks like this. So it still responds, but not nearly as well. So this positive feedback loop enhances the activity for a meaningful stimulus, for the stimulus which this cell is designed to detect. Yes?
Have they ever actually done that, like on a...
Sorry, what?
Have we ever actually done... I'm assuming we've just done this like with neurons, like measuring the electrical impulses.
Yeah.
So, like, asking or determining whether they can see...
You mean the people... Nobody, well, sorry. Of course, this kind of experiment, in any case, has to be done in a non-human animal. And this, I do not believe, this experiment could perfectly well be done by inactivating that pathway, but to my knowledge, it hasn't been.
Okay, but on animals, it's done by measuring the electrical signal, not...
This was done by measuring the electrical signal. You could also do a psychophysical, a perceptual experiment and see whether the person could actually see it, or the animal could actually detect it better. That has not been done, though, I don't think. But it could. Okay, you're obviously getting restless. Goodbye.